Hello guys, in this video we will be learning about 3D geometric transformations, 3D translations, rotations and scaling, and then we will also be discussing about OpenGL functions for geometric transformations. So as we have seen in 2-dimension, so if you're going for 2-dimension, usually the matrix that we would take is either 2x1 or 2x1 for a point and 2x2 for transformation matrix. And if we want to go for a homogeneous representation, then we would represent a point P in 2D as x, y and 1. Similar to that, our transformation matrix will be of size 3x3 in 2D, right? So exactly the same way, if you are talking about 3-dimension, we add one more coordinate to the 2-dimensional coordinate system, that is the z coordinate. So if we just talk about 3 dimensions, 3-dimensional representation, that is x, y, z as a point, then we use only 3x1 matrix. The transformation matrices will be of size 3x3. However, when we want to represent them as homogeneous coordinates, then we represent the point as 4x1, that is x, y, z and 1, and transformation matrix, any transformation matrix will be of size 4x4. Now, like 2-dimension, we can perform all 3 basic transformations even in 3-dimension, but there will be slight changes. Those, especially in terms of rotation, those changes we will be looking into now. So this is a 3-dimensional translation. So if we have a point here called as xyz, the problem would be to move this point along x-axis by some tx amount, along y-axis by some ty amount, and along z-axis by some tz amount. And when we add these offsets to the original coordinate position, we get a new point at translated at new position, and we would usually call it as p dash, and this would be our p. These are the equations of the 3D transformation transformation. Now when we look at the matrix for this, the matrix would look like this. This is tx, ty and tz. If we multiply this matrix with this point, a point generally in any of the point, then what we would get is the offset of tx is added to x, the offset along ty is added to y-axis is added to y, offset along z-axis, that is tz, is added to z, and the result will be the new point. So t is the notation that we use to represent this matrix. So this matrix again is in homogeneous coordinates. So technically speaking, it's okay if we have this matrix like this, x, y, z plus tx, ty and tz. This will be fine, but the problem is when we go for concatenation of operations, concatenation of matrices in order to get composite transformations, then it would be nice, it would be simpler for us to derive a single matrix if we represent everything in terms of matrix multiplications. Now apart from translation, every other transformation matrix needs multiplication in order to achieve that transformation, but only translation can also be achieved using addition. Now, to avoid this addition and to represent this operation in terms of multiplication, we go for homogeneous coordinate representation, and therefore the matrix homogeneous representation of translation matrix looks like this. Moving forward to our 2D rotation. Oh yeah, before that, let us say I have, this is a point transformation. Now let us say I have an object like this. Then how about translating this object? This is in 3 dimension. How about translating this object to a newer place? In that case, what we can do is we take the vertices of these of this object, which is used to define this object. We apply the translation matrix on all these points. So by applying that, we would get these points somewhere here, and then we connect these newly translated points exactly the way we have connected these points in its original object. So when we connect all of them, or when we write the object using those vertices which are newly translated, we get the original object translated to the new position. So moving forward to rotation, say suppose I have an object. Imagine I have my 2-dimensional representation like this. This is a 2D scene. If I have an object here, if I apply my 2D rotation, this object would move something like this around the origin as a reference point. Now if I want to move this object around a fixed point, around this fixed point, then my object would move around this fixed point like this, right? Now if you see here, this object is rotating around this fixed point, or the object is rotating around this origin. Now we will just look at rotating the object around the origin. In that case, it is similar to you are basically rotating your object around z-axis, right? So if you have this object as x comma y, the x dash comma y dash is something over here. After rotation, let us say you add a z here. Over here, your z dash will be same as your z. You are not changing the z of the object, you are only changing the x and y of the object. It is, the object is in still the same plane of the z. That's why the z is unchanged, right? So the same concept we take it further in 3D. So basically 2-dimensional rotation is just a special case of 2-dimensional rotation is just a special case in 3-dimensional rotation. We can consider it like that. As I said, now similar to how we rotate the object in 2D around origin or a fixed point, in 3D we rotate the object around a reference axis, right? That reference axis can be the base axis of the coordinate system, or it can be some other axis somewhere, the imaginary axis in the coordinate system, right? But as a basic rotation in 3 dimension, we will be looking at rotation of the object around the principal axis of our coordinate system, that is x around x-axis, y-axis and z-axis. To start with, we will look at rotation around z-axis. Now rotation around z-axis meaning to say, you have an object, once you rotate it, the object will still remain in the same z plane as like our 2D rotation, right? The z coordinates of that object will never change, only the x and y coordinates of the object changes. For example, let us say in this image, I have a point here, and this point has x comma y comma z. Now once I rotate this point, the point has moved to this place, right? This new position has its x changed, y changed, but my z-axis value will still remain the same. So if I consider the new point as z dash, then my z dash will always be same as my old point's z coordinate value if I am rotating my object around z-axis. So that's how, if you see here, I am rotating this object like this. So I am rotating it around z-axis, right? So that's the basic idea of rotating this object around the z-axis. So I will be rotating it like this while you are looking towards the origin from the z-axis. Now, since only x and y axis coordinate positions I am changing and the z I am keeping is the same, this is something similar to our two-dimensional rotation. So the x axis values changes using this equation, the y axis value changes using this equation. These equations are same as our 2D rotation equation, and the new axis, that is z axis value, remains unchanged. Now if I have to represent this as a matrix, then this is the matrix that I would use. Since I am rotating around z-axis, I want z-axis values to be same. So I am setting my z-axis to identity. That is, the third row and third column is set to 0 apart from the diagonal elements. Only the diagonal element in the z-axis, that is intersection of third row and third column, is set to 1. So third row and third column represents x, fourth row and fourth column represents homogeneous coordinate, second row and second column represents y-axis, first row and first column represents x-axis. So that's the notation that we will be moving ahead with. Okay, so if I multiply this matrix with this point, any point whose coordinate value is x, y, z, then what I would get is the result x dash, y dash and z dash. What I get will be same as what is there in this equation, in these equations. So this rotation is actually rotation around z-axis. So it is denoted using this symbol called RZ of theta. So the subscript z here represents that we are rotating the object around z-axis, and theta is the angle of rotation. And again, as we already seen the derivation in 2D rotation, when I apply this matrix, the rotation happens in anti-clockwise direction. So now this is about rotation around z-axis. Now what if I want to rotate around x-axis? That is, if I want to rotate this object like this around x-axis, or if I want to rotate this object around like this around y-axis. So in this case, what about it? How should I go about? For that, we don't have to look at the derivations how we have done in 2D rotation. We don't have to do that. As far as we know this z-axis equation and matrix, we can easily get the x-axis rotation equation and matrix and y-axis rotation equation and matrix. So to get that, what we have to do is we have to rely on something called as cyclic permutation. So what is cyclic permutation? Cyclic permutation is, so we know that this is a set of equation which will give us z-axis rotation. Now in order to rotate this object around x-axis, you have to perform one cyclic permutation. In order to get y-axis, you have to perform another cyclic permutation, like that. So what do we mean by cyclic permutation? Cyclic permutation meaning to say that values of x in an equation is changed to y. So the y is changed to z and z is changed to x. Once if I change this notation, I would have performed one cyclic permutation. So replacing x with y, y with z and z with x will give me one cyclic permutation. If I repeat this, that will give me second cyclic permutation. I can keep on doing that. Now if I apply the cyclic permutation on z-axis rotation, then I'll have to change the equation. Before that, this is z-axis rotation. If I apply cyclic permutation, this z-axis has to be changed to x-axis. So what I get as a result of this is x-axis rotation. Now x is changed to y. Similarly, my y is changed to z, and y is changed to z again, x is changed to y again, and y is changed to z, and z is changed to x. So if I perform this is the set of equation that I get. You would have seen here I am keeping x dash as x, so I am not changing x value in rotation around x axis. I am only changing y dash and y and z value of the coordinate position of the object. The x coordinate position of the of any point in the object will still remain the same. So now if you see here, this is a rotation around x axis. The object is rotating like this. This object, if you move here, only y-axis and z-axis value changed. The x-axis, if it is at this position, then also this would also be at the same x position. Both of them will be at the same x position. That's the idea behind this rotation, right? Now I can perform cyclic permutation again on this equation. What I would get is y-axis rotation. So we will see all of them together. Now this was z-axis rotation, and these are the equations. I perform x to y, y to z, and z to x permutation. Once I change it in using this cycle, what I get is x-axis rotation. I perform this again on this equation. On this equation, if I perform, I would get this, and on this equation, if I perform, I would get this. Right, this is rotation around y-axis. If you see here, my y dash is same as y, but x and z only I am changing. This diagram gives us this figure helps us in understand the rotation around y-axis in a better way. This object is moving like this around y-axis. Now we will see how this matrices look like. So since I would be rotating my axis, rotation axis is around x-axis, I am setting my x coordinates row and column to 0, and the identity, the diagonal element to identity. After that, I am just moving these values over here, right? So I am just moving this submatrix to this place. So this gives us rotation around x-axis, which is denoted by rx of theta. X here represents we are rotating the object around x-axis. If you take point x, y, z and 1 and try and multiply these two matrices, then we should be able to get these equations. We will get these equations. Now similarly, since this is rotation around y-axis, the second row and second column I set to 0 except the diagonal element. The diagonal element I'll set it to 1. I am setting it to 1 because I have to retain y as a result, as a value that has to be stored in y dash. Now for x dash, the z element is sine theta, that's why this is sine theta. X element is cos theta, so that's why this is cos theta. Similarly for z dash, the x element is minus sine theta, so this is minus sine theta, and z element is cos theta, and this is cos theta. So one small thing that you have to observe here is if you take this values, the first row, the sign in the first row will get the negative value or the minus symbol is attached to always in these x-axis rotation and z-axis rotation for the sign in the first row. However, over here the sign in the second row gets the minus symbol, not the first row. That is because in this equation the x-axis component is minus sign and that has to be stored as z dash. So we would be multiplying this with the z value. So once we multiply this with z value, we need x into minus sine theta plus z into cos theta. So that is what we would need. That's why this second row, the sign in the second row will get the negative value and the negative symbol. And the notation for this rotation or this matrix is Ry of theta. So this, guys, is about three-dimensional rotation. Moving forward, we will look at 3D scaling. So similar to our 2D scaling, 3D scaling is also is represented by multiplying the scaling factor of x-axis along x-axis with x coordinate, scaling factor along y-axis with y coordinate value of the point, and scaling factor with z-axis with z coordinate point of the z coordinate value of the point. Now in x 2 dimension we were only using x and y. Over here we have added that z coordinate also. That's the only change that we see. If you see here, even in the matrix, this third row and column for z axis is what is added additionally. So this S is the symbol that we represent to denote this matrix, and the behavior of the scaling factors Sx, Sy and Sz still remains the same. So if Sx, Sy, Sz values are same, then we would get uniform scaling. If not, we would get differential scaling. And if Sx, Sy, Sz value is more than 1, the object gets size of the object gets increased, not just increased, it move away from the object's original position with respect to origin, it moves away. Then if the value is less than 1 and greater than 0, if it is between 0 and 1, then it reduces, the size of the original object reduces and it moves towards the origin. So the characteristics of scaling still remains the same in 3 dimension as well. Moving forward, so this is about 3-dimensional scaling. So moving forward, we will look at OpenGL functions for geometric transformations. So the very first function that we are going to look at is GL translate. So GL translate is the function that we use for translation. Now this f, meaning to say the parameters that you pass inside are treated as floating values, floating point values. Instead of this, you can also use GL translate D. If you use GL translate D, these values will be considered as double values. Now Tx, Ty and Tz values are offset values with respect to x-axis, y-axis and z-axis. These values, the matrix will be, if you use this function GL translate F or GL translate D, the matrix will be automatically built by your OpenGL. And then the next function we use will be GL rotate F, or we can also use GL rotate D. So this function takes 4 parameters: theta, x, y, z. So theta is the angle of rotation. So let us say if I write 90 degree, so we are intending to rotate the object by 90 degree in anti-clockwise direction. Now the second thing that we would like to give is the axis of rotation. The axis of rotation can be specified by setting some axis value to 1. So if I write 90, 1, 0, 0, it rotates the object around x-axis by 90 degree. If instead of this, if I write 90, 0, 1, 0, then this would rotate the object around y-axis. Similarly, 0, 0, 1 rotates the object around z-axis. If I have 1, 1, 1, then it rotates the object around x-axis and then around y-axis and then around z-axis by 90 degree each. Then we have GL scale F. We can also use GL scale D. The parameters that we pass in this function is the scaling factors, that is Sx, Sy and Sz, these factors. So if we keep it as 1, 1 and 1, then the object's size remains the same and it will be in the same position. If I keep 0.5, 0.5 and 0, then the object size becomes exactly off in all directions. So around x-axis, along y-axis and along z-axis, the object size gets reduced to half, and we will see the object size reduced by half, and it will be uniform scaling. If I write 1, 2, 3, then the object size along x-axis will not be changed, and object size along y-axis will be doubled, and object size along z-axis will be tripled, and it will move away from the origin because it's more than 1. You're increasing the size, right? So that's the reason. So this, guys, is about OpenGL functions. Now we will see a small demo on these OpenGL functions. Now this is a program where we take one triangle and a point at the origin just to see the effect of rotation, right? Or just to mark the origin as a reference point, I have just put a point here, and we try and rotate this triangle and scale it or translate it, and we will see how we can do all this using OpenGL functions. Now we have already tried the same program in a similar program. We have already tried and understood how to rotate it around the origin and around a fixed point. So you guys can refer that in our my video of OpenGL implementation for 2D rotation. This is the same program which is taken but slightly modified. So this program is for triangle rotation, and I have taken a viewing window of -500 to 500, -500 to 500. So the rest of the code is same. I'm not taking any thetas or h and k's and etc. I just have a function called as draw triangle. In display, I clear the background, and then I am setting a point at 0, 0. This GL point size actually is used to add more pixels to a point. Though you plot one point, each point size, it basically acts as a thickness of your line you are drawing. So whenever you plot a point, the point size becomes bigger. So if I want to see my point size to be bigger, I have added more, the weight of the point is more here. That's why it appears bigger. And then I am drawing the triangle. So drawing triangle, this part of code is similar to your triangle rotation program. I rotate my object. I got this. This is my origin, and this is my object. Now to rotate it, what I have to do is, the function for rotate is called as GL rotate F. See, these are the arguments that it takes: GL float angle, X, Y and Z. So this X and Y and Z takes the value either 0 and 1. If you don't give 0 and 1, if you give something else also, it scales it to 0 and 1. So the first parameter that it takes is the angle, and the second parameter is the around which axis you are supposed to rotate. That is what it takes. Since this is 2 dimension, the default rotation is around z axis, so I am not supposed to rotate it around x axis. I'm not supposed to rotate it around y axis, but I am supposed to rotate it around z axis. That's why I have set the z parameter as 1. And one thing you remember, I perform this rotation comes first and then the object, right? So that is what the flow would be. So you in OpenGL treat it like you're going from right to left, or you treat it like as if you're going bottom up. So the bottom should be the object. It draws the object first and then it rotates. So treat it like that. Now, so if you want your object to rotate it, first you are supposed to use the rotate function and then draw the object. So whatever object you draw below rotate function, that will be rotated. So rotate function applies to the object that is below it. So keep in your mind about that. If you see, it rotated by 90 degree. Our original object was somewhere over here. It rotated by 90 degree around z axis. Now to answer Ashwin's question, Ashwin, I can set 111. This rotates the object by 90 degree, first with x axis, then with y axis, and then with the z axis. Say suppose this is uniform rotation, that is the angle of rotation is same. Then if I don't want that, if I want with different angles around different axes, then I can do this. So this rotates the object around x axis by 60 degree, around y axis by 30 degree, and around z axis by 90 degree. Of course, if I save this and run it, you might not get proper output because this is not a 3D program. You won't get to see as I said, you won't get to see the object because you don't have it in the plane that you are visualizing it. So that's why x and y axis rotation doesn't make sense for us in 2 dimension. But if you have a 3D object, you can of course do it. So this is about the rotation. GL, this F is actually the data type. You can change it to D also. I'm not sure if I is available. Float and double is for sure available. Translate F or translate D. So yeah, I integer is not available. Now this translate actually takes the tx value, ty value, and tz value. Now tz, I don't want any rotation. I don't want any translation. My object is, the first point is at 100, 200, right? So I will translate it to -100, -200. This should actually, yeah, if you see, my object is at the origin. So I can translate it with 200, 400 also. So I'll change it to -200, -400. Another point, the top tip of the triangle is at the origin. I can also scale using scale So this scaling also takes Sx, Sy and Sz values. Say suppose I want to scale it twice along x-axis, y I have to keep it same, z I have to keep it same. Then if you see along x-axis, my object becomes double. You can't see it because that portion is clipped. This is the clipping that happened. Your OpenGL automatically have applied clipping with the clipping window. The clipping window that you have taken is -500 to 500, -500 to 500. Your OpenGL automatically clipped your polygon and got the intersection point with the clipping window, and it is displaying only this much. So this much portion of the triangle is not considered for pixeling or rasterizing at all. So I can perform scaling, uniform scaling like this. So it increased and moved away also from x-axis and along x-axis and y-axis. It has become bigger. So let's say it is 0.5 and 0.5. The object became smaller, not just smaller, it is moved towards the origin. So that's also can be seen. So that is those are the three functions that you use: GL rotate F or rotate D, GL translate F or translate D, GL scale F or scale D. That's about it, guys. Thank you.